Welcome to another custom-tailored deep dive.
Yeah.
Today we are jumping into something that is, well, it's going to affect you directly if you're studying the CompTIA SecAI Plus material.
Right. Specifically, Section 18, which is all about AI encryption and data safety.
Exactly. And, I was thinking about this before we started. If you want to secure a traditional computer network, you basically build a medieval fortress.
Yeah. You build a wall.
Right. You construct a massive stone wall, you dig a deep moat, you write a firewall rule, and when a packet of data arrives, the system just looks at the signature and says, blocked.
Yeah, it's totally binary.
Yes, binary. It's deterministic.
Yeah.
And honestly, it is incredibly comforting. But the moment you step into the world of artificial intelligence, that comforting rulebook just, well, it goes up in flames.
It really does. Because you aren't defending a static stone wall anymore. You're trying to secure this probabilistic, constantly evolving intelligence.
Right.
And the reason everything changes is because that intelligence is fundamentally dependent on its fuel, which is the data.
The data is everything.
Exactly. If you compromise the data, you compromise the model itself. So the architectural challenge we face today, and this draws really heavily from the SecAI Plus frameworks, is how to protect massive volumes of data without breaking the underlying mathematics that the AI needs to actually function.
Which is wild when you think about it. It requires completely tearing down that fortress mindset.
Oh, absolutely. You have to build something entirely new.
I think the assumption for a lot of people, outside of data science, is that AI just reads the entire internet and magically figures out how to spot a zero-day exploit.
Right, like it's just this omniscient brain.
Yeah, it feels completely autonomous to the end user.
Well, and unsupervised learning certainly exists, but for high-stakes, highly precise tasks like enterprise security classifications, the foundation is supervised learning.
And supervised learning requires a staggering amount of human labor. Right.
A mind-numbing amount. You have to feed the model millions of files, and human analysts must painstakingly pre-tag every single one of them.
Like literally sitting there saying, this file is a Trojan, this file is a benign system update, this file is ransomware.
Exactly, file by file.
Okay, let's unpack this for a second. That sounds like a terrifying bottleneck, because humans get tired.
Oh, humans are the weakest link. They click the wrong button all the time.
Right. So if an analyst accidentally tags a piece of malicious ransomware as, benign,
Right.
what happens?
The AI learns the wrong underlying mathematical characteristics for what constitutes a threat.
Oh, wow.
Yeah, the industry calls that data poisoning. The model starts letting that specific malware bypass your defenses in the real world simply because, well, you explicitly taught it to.
So it's that classic garbage in, garbage out paradigm, but operating at machine speed.
Precisely.
Let's put this into a real-world scenario. Maybe it's something you'd see on the exam. Imagine you were configuring a classification pipeline for a massive enterprise spam detection model, and you have terabytes of emails to ingest. How do you verify the human labels without grinding the whole pipeline to a complete halt? Because relying on one person per file seems completely reckless.
It is reckless. You build a layered defense. Before any human even looks at a file, you have automated schema and type checks running in the background.
Right, just quietly stripping out corrupted or empty data.
Exactly. Get rid of the absolute junk first. Then you implement layer 2 human verification, and specifically, you want blind double labeling.
Blind double labeling. Meaning two independent reviewers are analyzing the exact same file without seeing each other's work.
Yes. They operate in complete silos. If both reviewers flag the file as spam, boom, the label is accepted.
But what if they disagree? Like one says spam, the other says benign.
Then an adjudicator steps in.
Ah, I see. A tiebreaker.
Right. The adjudicator resolves the discrepancy based on strict organizational guidelines. And only after the adjudicator breaks the tie does that verified dataset actually get ingested into the AI training environment.
That makes a lot of sense. Because automated scripts, they miss subtle biases and weird edge cases, right?
They miss them constantly. Building human consensus is really the only way to insulate the model from that data poisoning.
And it forces a critical evaluation of the data itself, I imagine.
It does, which actually opens up a completely different problem.
What's that?
Well, you've painstakingly labeled terabytes of data. The instinct of literally any data scientist is going to be, great, let's keep all of it.
Oh, sure. More data means a smarter, more nuanced model.
Right. They want to hoard every possible variable just in case it becomes useful later.
Because you never know, right?
From a pure data science perspective, yeah, more is always better. But from a security and compliance perspective, excess data is a massive liability.
Which brings us to data minimization.
Exactly. The core principle of data minimization dictates that you must only collect the absolute minimum data required to achieve the stated purpose of the AI.
Okay, let's test that principle with another scenario. Say you're building a predictive maintenance model for a massive corporate office building,
Okay.
and you want the AI to predict optimal HVAC temperature settings
Okay.
based on employee badge swipes.
Sure.
So you pull a data set, and it includes, so let's say, the time of the badge swipe, the floor number, the building zone capacity, the employee's social security number, and their home address.
Well, right there, ask yourself what the AI actually needs to predict the temperature.
Right. It needs to know how many bodies are on a specific floor at a specific time.
Exactly.
It absolutely does not need to know where those bodies live or what their tax identification is.
So you drop the home address and the social security number before they ever enter the training pipeline.
You just delete those columns entirely.
Yes, you retain the swipe time, the floor number, and the zone capacity, because an attacker cannot exfiltrate data that you never collected in the first place.
Wow. Yeah, you are mathematically eliminating the attack surface.
It's the ultimate proactive control. And if we connect this to the bigger picture, consider the threat of generative AI hallucinations.
Oh, that's a huge issue right now.
Huge. But a large language model cannot accidentally leak a factory worker's home address in some probabilistic text generation if that address was never ingested into the model's weights to begin with.
You cut the liability off at the source.
Exactly. And for the minimal data you do retain, it must be deleted as soon as its usefulness expires. Short retention periods are key.
Right. Okay, but we can minimize all we want, but inevitably, highly sensitive data simply has to enter the pipeline to make the model useful.
That's true.
Like healthcare models require medical histories, financial models require transaction records. We have to hide the identifiable parts of that data, and I know this is a massive trap for compliance audits.
The redaction versus masking debate.
Yes, the technical distinction between data redaction and data masking, because people use the terms interchangeably all the time.
And confusing those two will completely break an enterprise data pipeline.
Okay, break it down for us.
So data redaction is the structural destruction of information. Think of it as the digital equivalent of taking a thick black Sharpie to a physical document.
Okay. So let's say an automated system is processing legal transcripts to be published in a public repository.
Perfect example.
And the system encounters the sentence, the witness, John Doe, resides at 123 Main Syndica. Redaction means I programmatically replace the name and address with a glaring, obvious text marker.
Yes.
So the output becomes the witness, bracket redacted bracket, resides at bracket redacted bracket.
Right. And the goal of that structural destruction is really twofold. First, obviously the original data cannot be read. Second, anyone looking at the file explicitly knows the information was deliberately removed.
Which makes it the perfect tool for like public document releases or FOIA requests.
Exactly. But consider what that does to an automated database pipeline.
Oh, right. If I am building a testing environment for developers and the application code is explicitly expecting a standard first name, last name format.
Or a 10-digit phone number.
Right, and it gets a text string of brackets.
No.
The system throws an error and crashes.
The schema fails completely. And that is exactly where data masking steps in to save the architecture.
So masking is different how?
Masking also removes the sensitive information, but its primary goal is to preserve the structural utility of the data.
Preserve the utility.
Right. Instead of destroying the shape of the record with a generic tag, you programmatically replace the real data with structurally sound fake data.
Okay, let's look at a staging environment scenario. Say the production database contains the field, phone number, 555-867-5309.
Okay.
The application has a strict 10-digit numeric validation script. If I hand the developers the real numbers, I fail the security audit.
Yeah.
But if I use a redaction string, the validation script crashes.
So you apply a masking rule that satisfies both requirements. You change the output to 000000000, or just a randomized 10-digit sequence.
Oh, I see. Or you use destructive substitution that maintains the format like, replacing all but the last 4 digits of a credit card with asterisks.
Exactly. It still looks like a valid format to the database, so the schema survives, but the sensitive information is totally obliterated.
Okay, that actually brings up tokenization, which I know is a very specific type of masking.
It is, but it's non-destructive.
Right. The system takes a 16-digit credit card number and replaces it with a mathematically unrelated 16-digit alphanumeric string, the token.
Right.
It preserves the exact length and format, but the crucial difference is reversibility, isn't it?
That's the key word. An authorized downstream payment system can securely exchange that token for the real card number when a transaction actually needs to process.
So redaction and basic masking destroy the original value permanently.
Right.
But tokenization hides it while keeping a highly secure map to reverse it when necessary.
Exactly. And reversibility is the entire battleground when we talk about privacy laws.
Oh, I bet. Let's say data scientists need to track the exact same user's activity over time across multiple different data sets without actually knowing who the person is.
Like a long-term medical study analyzing treatment efficacy?
Perfect.
So engineers typically use pseudonymization for that tracking. You take a patient's real name and replace it with an alias like subject 8472.
Right.
And everywhere that patient appears across 5 different databases over a 10-year period, they are consistently labeled subject 8472.
So the AI can correlate the records and find longitudinal patterns without exposing the person's actual identity to the researchers.
Correct.
Okay, but let's put on our auditor hats for a second. Say you are auditing that healthcare AI dataset for privacy compliance.
Okay.
Dataset A replaces patient names with a highly advanced cryptographic hash. The salt and the decryption key are secured in an air-gapped vault managed strictly by the chief medical officer.
Right.
So I can track the hash over time. Does that dataset clear the requirements of the General Data Protection Regulation, the GDPR?
No. The moment you retain a key, you've built a ticking time bomb for an auditor to find.
Wait, really? Even if it's air-gapped?
Even then,
Right.
under strict regulatory frameworks like the GDPR, pseudonymized data is still legally classified as personal data.
Because somewhere on a server, that mapping key exists. The process can technically be undone.
Exactly. Reversibility is a massive mathematical liability. If it is reversible, the law treats it as personal data.
Wow.
It remains subject to all the strict handling, auditing, and deletion requirements.
So what does this all mean for total privacy? How do we escape the regulations if an organization just wants to train a model without taking on all that legal overhead?
Well, let's look at a different approach. Take dataset B. Patient records are aggregated into demographic blocks like males 3040 in zip code 90210,
Okay.
and all original individual records and any associated cryptographic keys are permanently wiped from all servers.
That is true data anonymization.
Yes, you have mathematically destroyed the link to the human being entirely. No one, not even the original engineers, could ever figure out which record belongs to John Smith.
And because the connection cannot be reversed, it ceases to be personal data.
Exactly. It falls completely outside the scope of most privacy regulations. The legal distinction hinges entirely on whether the process can be undone.
That is such an important distinction for anyone taking the exam to remember.
Absolutely.
Okay, so we've stripped out the unnecessary data through minimization. We've faked the schemas with masking so the databases don't crash.
Right.
And we've wiped the mapping keys to ensure true anonymization. But at the end of the day, these files still physically exist on a server somewhere, right?
They do.
If someone kicks down the door to the data center and steals the hard drives or breaches an S3 bucket, none of that prep work matters if the files are just sitting there in plain text.
Which is why we have to lock the physical medium itself. We rely on data encryption at rest, typically utilizing the AES 256 standard.
Okay, but before we talk about how encryption interacts with the AI, we need to clarify what the AI is actually looking at.
Good point.
When an AI processes data, especially in a modern retrieval augmented generation, or a RAG application, it's not reading text like a human reading a book, is it?
No, not at all. It converts concepts into mathematical vectors.
Right, so think of it as mapping concepts as coordinates in high-dimensional space. The words king and queen end up physically close to each other in that mathematical space.
Exactly. The system calculates the distance between those coordinates to perform similarity searches and understand context.
Which raises a massive technical hurdle. How do you encrypt those coordinates without completely breaking the spatial math?
Well, what's fascinating here is that if you simply encrypt the vector database at the application layer, the coordinates turn into random noise.
The spatial relationship is just destroyed.
Right. The AI wouldn't be able to search it.
But it can search it because the protection happens down at the storage layer.
Yes. When the authorized AI application calls the database, the storage layer decrypts the file on the fly.
Ah, okay, so the application layer only ever sees the decrypted, perfectly preserved data.
Exactly. The mathematical vectors remain completely intact. The AI can perform its similarity searches and calculate the distances between data points without ever knowing the hard drive underneath it is heavily encrypted.
That's brilliant. Okay, let's play out a multi-million-dollar proprietary AI model scenario. We are defending against three specific attack vectors.
Let's hear them.
Scenario 1. An attacker physically steals the backup hard drives.
AES 256 encryption at rest completely neutralizes that. All they get is useless ciphertext.
Right. Scenario 2. An attacker intercepts the API calls between the database and the model.
We implement TLS encryption in transit to protect that network tunnel.
Okay, but here's where it gets really interesting. There's a third scenario that completely bypasses both of those defenses.
Ah, yes. Because when the AI is actively running in production, calculating billions of parameters, the CPU cannot perform complex vector mathematics on encrypted ciphertext.
It has to read the real numbers.
Right. To do the math, those multi-million-dollar model weights have to be decrypted in the system's active memory, the RAM.
Doesn't that open a massive window?
A huge one. You have just identified one of the most sophisticated attack vectors in modern infrastructure, the memory dump.
The memory dump.
Yeah. Traditional encryption is fantastic at protecting data at rest and in transit, but it leaves the data completely exposed while it is in use.
So if an attacker gains, like, root OS level access or compromises the hypervisor managing the virtual machines,
They bypass the vault door entirely.
they just execute a memory dump command and scrape the decrypted model weights directly from RAM.
Exactly. They steal the data while it's sitting on the active workbench.
Wow.
It is a devastating blind spot. Defending against it requires highly specialized hardware, like secure enclaves or confidential computing environments, to protect data while it is actively being processed by the CPU.
That is intense. This whole journey through the SecAI Plus material reveals a constantly shifting landscape, doesn't it?
It really does. It never stops.
We moved from the painstaking human consensus of double labeling to the ruthless discipline of data minimization. We learned the hard way that masking preserves structural utility while redaction destroys it.
And that retaining a mapping key keeps you firmly in the crosshairs of privacy regulators due to the liability of reversibility.
Right. True anonymization is the only escape there. And finally, we saw that even the strongest AES 256 encryption at rest cannot save an AI model from a root-level memory dump.
It's a lot to take in, but as we continue to build these incredibly complex systems that are increasingly designed to automatically patch vulnerabilities, hunt for threats, and respond to cyber attacks at machine speed, we have to confront a really difficult reality.
What's that?
Are we rapidly approaching a future where cybersecurity is entirely machine versus machine?
Oh, what?
A future where a zero-day exploit and the resulting memory dump patch happen in milliseconds, leaving human analysts completely out of the loop? And if so, who is legally and ethically responsible when the machine makes the wrong call?
That is a chilling thought to leave on. The speed of compromise is just completely outpacing human reaction time.
It is.
Well, taking this knowledge and applying it to your own environments, whether you are prepping for this SecAI Plus exam or sitting in a high-stakes compliance audit tomorrow, that is where the real work begins for you. Thank you so much for joining us on this deep dive.
Thanks for having me.
We will see you on the next one.